and the exam.
Good morning, Professor.
Good morning. All right, let's see. Um, okay. All right, so today is our last class. Hopefully, everyone will be ready for the exam on Tuesday. I have several good news, I think. Let's see. Let me just make sure I don't forget anything. Um, okay. So let me start with um, the grades. Let's start with the grades. Final grades. Um, so I had some people asking to, to make up work or to, they missed an assignment or something and they're hoping they can make it up or do something about it, right? So because it's very different circumstances and I always try to be fair to everyone, what I decided to do instead was to drop some of the points out of the classwork. So the total number of points right now, if you look at everything we did for classwork, questions of the day, quizzes, and wiki sets, homework assignments, whatever, everything that we did except exam 1, exam 2, exam 3, which is coming up, and quiz 4, which is added to exam 1, because remember that was extra credit for exam 1. So everything else is classwork. Classwork. Again, that's question of the day, questions of the day 1 through 3, quizzes 1 through 3, 5 through 7, so not quiz 4, and the wiki sets, which, this last one, and I'll talk more about the last wiki set. We kind of work differently, but I'll talk about it. So all of that is classwork. If you add up the total number of points that comes from that is 84, but I'm gonna do it out of 70. So that really means that I'm essentially, kind of dropping, it's not exactly that, but it's almost like dropping one assignment and making the questions of the day extra credit or something like that, So think about it the way that you want, but we'll make this out of 70. So this means that if you have over 70 points, you have some extra credit over there. If you have 70 points, you were actually missing 14, but it actually counts as 100% on classwork. Make sense? So this is to your advantage. So if you want to compute your classwork grade, what you do is add all these assignments, those, right? Divide by 70 and multiply times 100. So this will give you your classwork grade out of 100. Right? Okay. So for your final grade, as I stated in the syllabus, we have classwork counts 20%, and your lowest midterm is 20%, and your other two midterms are 30%. Okay, so if we call this, oh, Yeah, so if we call this classwork, okay, um, your exam one grade is actually exam one plus quiz four, because quiz four was extracted for exam one. So exam one is going to be exam one grade plus quiz four. And this is also out of 100. So if you actually did super good in the first exam and you try the quiz four, you might be over 100. Okay? So this actually adds up to 110, but it's out of 100. Okay? So what we'll do is an exam three, this also, it's going to be exam three. This is the only thing missing. And I'll continue adding grades to the wiki set 3. I did for everyone who sent me solutions earlier in the day yesterday. So I'm missing, I think, maybe 5 wiki assignments that I got close to midnight. So I haven't graded those, but I'm planning on doing that later today so that you can have all your grades. So your final grade is going to be um, okay, one way to do it, because of that 20% thing, you can do this exam 1 plus exam 2 plus exam 3 times 0.3, and then just subtract the smallest of exam 1, exam 2, and exam 3 times zero point 0.1. That really makes your lowest 20%. Okay? And then you add your classwork times zero point 0.2. Okay, and that's it. That's your pick. But we still don't have this one, right? And I guess what you want to know is what grade you need in the third midterm to pass the class, right? So many of you are that's what you really want to know now. So you need, I usually have my cutoff for a C or more at 70%. Since the first exam was really hard, I'm going to make it 65%. Okay? So you need 65 uh, or more for a C or better in the class. Okay, and so to have a to to know what you need to have a C or better in the class, what you could do is let's see. Assuming that you're gonna do better in in exam three than in the other two. We're gonna drop one of the other two. Um, what can I do? Yeah. So you can compute what we have already. You can do, let's see, your partial grade up to now is going to be all of that I have above, but without the exam 3. So exam 1 plus exam 2 times 0.3 minus the minimum of this. So take your lowest grade of the two, and then add your classwork. So if this is your partial grade, what you'll do is you'll do 65 minus your partial grade divided by zero point 0.3. You need at least that to get a C or better. Makes sense. And then I don't have the cutoffs for like exactly for the other grades, but let's see, because I usually, let me see, maybe I can do it right now. So if you want to know how to get uh, an A is usually 90 here. It's gonna be probably 89, but I haven't computed that, okay? Because I just lowered it. I just wanted to let you know the 65 cutoff. But so an A is usually 90%. So you will change the 65 to 90 to get an A. Although I think it's gonna be a little lower, so maybe 89. All right. If you want to be is close to 80, it's probably going to be a little bit lower than 80. But the one that's definitely guaranteed is 90, 80, 70 for A, B, C. But I lowered the one for C, so that means that the ones for A and B are going to be a little lower as well. I just haven't decided exactly because I just wanted to get that 65 for the passing one, right? So, but if you want to know, the guarantee A is a 90, guarantee B is an 80, guarantee C is a 65. But again, A's and B's are going to be a little bit lower. Make sense? Hopefully that helps you. And so it's everything's clear. You know exactly how you're going into exam three, and now I can talk about exam three. Any questions so far? All right, so I'm just gonna say here, guarantee A is an 90, and guarantee B is an 80. So guarantee C is a 65. So it's actually going to be a bit lower, but I cannot tell you the number right now because I haven't. I just decided on the 65. So it's probably going to be 89, 79. But that's where you can replace these by any of those, and that will give you an idea if you're going for an A. Substitute for a 90 or 89. Okay. Any questions about that? Okay. So now the exam. Oops. So we'll go over the homework after. So for exam three, it is on sections H and H. Section H of the graph theory book, so that's planarity. And section H of the combinatorics book, that's what we've been doing lately. Polya's counting method, that's from the combinatorics book. So for the exam, it's going to be 50% Polya's, 50% planarity. For Polya's, I'll give you a problem similar to the 11 problems in the wiki sets, and I'll give you the form. So you really have to complete one of those forms. So starting with Polya's. So 50% is Polya's. You need to complete a form. I'll add it as one of the pages of the exam, so it's handy. Mm-hmm. And then essentially, it's going to be 30%. So what should I say? Yeah, so this is out of this 50, right? So 30, a little bit more than half, is going to be the transformations and cycle codes. So like what I was expecting for the first part of the assignment, right? So you can think about it as a table. You know? What transformations, what are the monomials, the cycle codes, right? And then um, and then 10% is going to be the polynomials. So once you have your cycle codes, what are the polynomials? Now, I am actually breaking it like this because even if your cycle codes have a small mistake, if you're consistent, you can get this full 10%. Make sense? So maybe your cycle codes, one of your cycle codes has a wrong exponent, right? If you're consistent in translating that into the cycle polynomial, cycle index polynomial, so that's going to carry that mistake, obviously. But if you're consistent with that mistake, then you can get the full 10%. Okay, and same thing for the other 10% is the colorings. So the actual where do you substitute what number? If you have two colors, just substitute two in the cycle in the cycle polynomial, right? Or if you have 5 of one color and 4 of the other color, you use the pattern inventory. You need to find the coefficient of some, right? So that's going to be another 10%. And again, even if there are mistakes in the first part of the problem, as long as you're consistent, then you can get this full 20%. That's why I'm breaking it up like that. That would give you a better chance. Otherwise, if you make a mistake at the beginning, everything else is wrong. Okay? So that's Booleas. And then the other 50% is planarity. And okay, and for that, we're gonna have out of that 50%, yeah. So 20% is going to be Euler's characteristics. Euler's formula. Remember all the first problems in the quiz in quiz 7? Euler's formula, degree theorem, the regional degree theorem, and that note. Remember that I told you can use these 4 things to kind of play with all the variables. Sometimes you're given the number of vertices and something about the degrees, or you're given some information and you kind of put these 4 things together. Maybe less than those 4, but you should always consider the 4 of them in those types of problems and kind of working with the variables V, E, R, vertices, edges, regions, or phases, and the degrees or regional degrees, whatever is given to you, you kind of try to put all of that together to get to whatever is needed. Either you're asked for one of those numbers, or write one of those numbers in terms of the other numbers, or prove an inequality, right? And you can go with the first few problems of the quiz 7 solutions. Yeah, was that quiz 7? Yeah, I think that was the previous homework, the planarity. I think we had it in the form of a quiz, but you have the solutions to all those problems. And I will also go over the notes, because in the notes we solve some other problems that were not part of the homework. So I will definitely go over the exercises, the examples, the problems that we did in class. Mm-hmm. And then 3% is going to be proving that a graph. So I'm going to give you 2 graphs. One is planar and the other one isn't. So prove that a graph is planar. So to prove that a graph is planar, you need to just give me the drawing that doesn't have any crossings. And you also need to prove that another graph. And I'll tell you which one is which, so you don't have to decide. Prove that a graph is not planar. And to prove that a graph is not planar, you can choose. You can use the, finding a subdivision, a K33, K5, or subdivision of K33 or K55, or you can use the Hamiltonian cycle. So I'm just going to call it the Hamiltonian cycle technique, or finding a K33, K5, or subdivision of K33 or K5. Now, I think that many people prefer the Hamiltonian cycle technique. I'm not sure, but just please be very careful to actually state, what is your Hamiltonian cycle. Draw it. Let me know the order of the vertices in the Hamiltonian cycle, and the order in which you are adding the edges, because that really makes a proof. If you don't give me that order, then I won't be able to give you the points, because if the way that you're adding edges is not forced, meaning, you add an edge and then you say, oh, this other one, let's say that one is inside the cycle, right? In the interior of the cycle. And then you say, oh, this other one, to avoid crossings, needs to be in the exterior. But if that second edge that you're adding could actually be added to the interior without a crossing, then you're losing generality. And if you eventually get a contradiction that there is a crossing, then it doesn't work, because maybe if you had gone the other way, you had two possibilities, being inside or outside. If you had been the other way, maybe there is a way to draw it, right? And since I already told you there isn't a way, then you're obviously looking for that contradiction, but that wouldn't be a contradiction because you forgot to follow the other branch, right? So if you decide to use the Hamiltonian cycle technique, be very, very, very careful to, give me, label everything, give me exactly what's the Hamiltonian cycle and the order in which you are adding the edges. Otherwise, it really makes me feel bad to say, oh no, but this doesn't work, and essentially, I cannot give much partial credit. So please be aware of that. For the K33 and K5 or the subdivisions, we have plenty of examples. You can look at the solutions, how you can state, how you can draw your graphs or, your subdivisions on top of the original graph or next to the original graph, all the labels and everything. So just make sure that you make it very clear what everything is, what are the vertices of that K33 or the subdivisions or whatever it is. All right?
Question. When a graph is complex, it's like trying to do the Hamiltonian cycle. Mm-hmm. It may be difficult to try and squeeze a number to say, I'm going from this vertex to this vertex if the lines crisscross each other. So would you want us to list the edges and then write the number against it? That way then you could follow the path. I would also maybe use a highlighter to try and trace the path, maybe.
Yeah, you can always write on top of your graph, but if you're using the Hamiltonian cycle technique, what you should really do is draw that cycle in a different place than your original graph, because it's hard to do it on top of the graph. It's easier to have the subdivisions of K33 or K5 on top of the graph. But for the Hamiltonian cycle, your graph can look, I don't know, it can be very crowded here. And it could be hard to actually, highlight the Hamiltonian cycle. So what you really want to see is almost like a big circle right here with the labels of the vertices that will make your Hamiltonian cycle. So if you go from something very crowded to saying, A, I don't know, G, C, H, you label them in any label you want, or maybe give you labels. So if I already give you labels, then just let me know what is that cycle, right? So if you draw it I don't know, if you draw something like this, it's very, very clear what your Hamiltonian cycle. You don't have to write it.
Yeah, it's like that. I thought you just meant like a list of one here followed by two, the here, and then I would have followed that same path here.
Yeah, and so it's better to have it here. I mean, you can probably play with your original drawing, but usually, the idea of using a Hamiltonian cycle is that it kind of organizes things, right? So now you have this big circle, that represent the Hamiltonian cycle, and now the rest of the edges need to use two of the vertices on that cycle, and so they can be completely inside or completely outside, and that's kind of the technique. So you really want to go from whatever picture I give you to these, something like that. I'll give you labels so that it's easy to refer to the picture. Okay, so I probably just try to have that, like almost like in order from top to bottom, so that it's easier to to see what the labels are. And then you can just draw your Hamiltonian cycle with the appropriate labels. If you remember, if you go back to the notes for this topic, I usually leave the missing edges, right? The ones that are not part of the Hamiltonian cycle that were part of the graph, so I still need to draw. So I kind of make the list of those. I don't know. And then again, if you look at the notes, I numbered these ones in the order that they are added to my picture to get the contradiction. But for example, if let's say I'm adding CV here, my second one, J, GJ could be my second one, because if I don't want crossings, then I'm forced to draw that one outside. So that could be a second one. But let's say JH, if you label this one as 2, that's my first one, CV. If I label JH as 2, then that doesn't work, because if you decide to have it inside, you're only following one of the two possibilities. Having it inside or having it outside is possible. And so, in principle, you need to follow those two cases. If you wanted to add that one as a second one, you need to say, okay, if it's inside, this happens. If it's outside, that happens. So if you only do one of the two, then your proof is not. So 2JH cannot be your second one if you're following this method. GJ could be, because now GJ is forced to be outside. So I'll go by the order that you give me, and if all your moves are forced and eventually you find a crossing, your proof is correct. If at some point you are assuming that something is inside or outside, where it could actually be either way, then your proof is not correct. There is a part missing. And depending on how soon you make that mistake, if you do it at the very beginning, your proof doesn't at all. If you do it towards the end, you can get some partial credit. You could get a little bit of credit just like giving you can get some partial credit just like giving me that Hamiltonian cycle, but not a lot, because you haven't really worked with the lessons.
Would you want us to list all the possible paths? Like 2 here or 2 here, or one's fine?
No, just the one that you decide to use. Just the one that you decide to use. Just make sure that everything is forced.
Okay? Everything's labeled like this, basically?
Yeah, so make sure that if you decide to use an edge, it's because it only has one place to be, either inside or outside. Because if you put it in the other place, then it creates a crossing. That's what I mean by a forced move. You're forced to have GJ outside, because if you had it inside, you would create a crossing. So GJ is forced to be outside once you have the CV inside. And you always have the other possibility, right? The K33 subdivision, the Kuratowski's theorem, essentially. K33, K55 is subdivision subgroups. All right? Questions?
I have a question regarding the folias. Are you going to give us like one of the cubes, or it can be string, it can be any of those, right?
It can be any of those. We in the remaining time today, we can go over any questions you have for those forms. In the forms that I uploaded this morning, there are no pictures. Essentially, I think there are a couple of forms that have pictures because it's just the square. right? But we can go over questions over that. Now you know. Now it's going to be easier, I guess, because if I give you something about the cube, you already have the rotations, the transformations of the cube, even though they kind of apply differently to different problems, right? The patterns that you get are different for different problems. The rotations themselves are the same. Same for the tetrahedron.
We getting one cube, for instance, or we getting the cube. Also, we getting the string as well. It says a different.
Oh no, just one problem. So imagine I won't do this because you have all the solutions, but imagine I just select one of the 11 problems. So just one of them, just one.
Okay.
Yeah. So, and
I have a question, Professor.
Yeah.
I have a question about confusing about the pattern and combined cycle codes.
Mm-hmm. In the table, right?
Yeah, cycle codes. I have from when I don't understand why I have to use X1 and then why I have to use X1, X4, why not X1, X3? This is the confusing part for me. And for also the exponent, like 2, 6, 2, 12, 2, 3, those little bit confusing for me. I don't understand.
Right. For that, did you have any particular problem in mind? That I mean, I could just choose one and tell you about those questions. But do you have any particular one?
Particular problem? Okay, first, I think I need to understand the Q1. It will help me. Okay. Like age 77.
All right. Okay. So let me see. Are there any other questions about the format of for now?
For the complete the form, we're going to use the exact same form that you gave us, and we're just filling it out for the exam. And how many problems will be assigned to complete that whole form? How many problems? Would it just be just one? Okay, got it. Okay.
Just one problem.
Okay. And will you be showing some of the homework problems that we did today? Okay, got it.
So, questions on the format of the exam so far, so that I can go to the homework problems.
For the and we're not going to have shapes that are not not the cube or tetrahedron, right? Just those two 3D shapes.
No, we could have other shapes, right? We have all the polygons. We have the squares. We have, for example, for the tetrahedron, we did the tetrahedron. So problem 79 is the actual tetrahedron, but 80 is spheres that kind of form a tetrahedron, right? So we could have, there's I think a problem in the book that has a triangle, but instead of a triangle, it uses circles that form the shape of a triangle. But it's the same as, so, I can have, now you know what to do with any polygon, right? So if I have a triangle, you have the symmetries of the triangle. You have the 3 rotations and the 3 reflections, and just make sure that you understand from the problem whether or not you're using rotations and reflections or just rotations, right? But if you know how to handle the triangle, the same rotations and or reflections apply to a problem where you have, for example, three circles, and you're gonna, paint each of the circles. Or if you have something like this, or a bigger triangle made out of circles. And the transformations for the triangle, the 3 rotations, three reflections, are the same for this one. And so if you are coloring the circles, you could still find the patterns. The patterns are going to be different if you are coloring, for example, the vertices of a triangle. If you color the vertices of a triangle, or if you color these 3 circles, if you're gonna get the same cycle codes. But if you have something like this or like that, your cycle codes are gonna be a little different. Here you're coloring 6 things, whereas here you're just coloring 3, here you're just coloring 3, here you will be coloring 10. But any of these problems will be of the same, it's the same symmetries. Mhm. If you think of the square, in class we talk about coloring vertices of the square, the sides of the square, coloring the 2x2, the little squares in the 2x2, coloring the little squares in the 3x3, and why not coloring the squares in the 4x4. All these problems are of the same, use the same transformations, the same rotations, the same reflections, but the patterns are different. Mm-hmm. So let's say, for example, if I were to do the 180-degree rotation and I'm coloring the vertices here, it will be A. When I rotate 180, this is A, this is B, and this is B. For this one, same rotation, 180-degree rotation, you get the same thing. For this one, you get AA, B goes to B, C goes to C, B goes to B, E goes to itself. For this one, when you rotate 180, A goes to A, B goes to B, C goes to C, D goes to D, E goes to E. Now, they go to the opposite. But you can check it, right? You can take that square, rotate it, see where this F goes to, and label the other one F. G goes to G, H goes to H. Uh-huh. So your pattern, your cycle codes, and this goes to Farida's question. For your cycle codes, you have, you have X, C, E, let's say. E is the exponent. Maybe I'll do X, I, E. Okay? So this I is the number of repetitions. And this E is the number of letters that repeat I times in the pattern, right? In a pattern, to go from a pattern to the cycle code or the monomial, to go from the pattern to the cycle code, this is what we use. Mm-hmm. So that helps in any of the problems, Farida, and I think that's what you were asking. So the subindex is the number of repetitions. The exponent is the number of letters that repeat that number of times. So in my example, for all of this, for the square, if we were doing the 100, you have one pattern per transformation, right? And in this example, I'm doing 180 degrees for different problems. So this one is if you were coloring the vertices of the square, if you were coloring these little squares, these little squares, these little squares. I could add, for example, coloring the edges, if you want to color, if you want to color the edges, or let's say that you want to color the edges. You have A, you rotate 180 degrees, that's an A. B, you rotate 180 degrees, that's a B. You rotate 180 degrees again, it brings you back to the B. Mm-hmm. And so for any of those in my example, so I'm using, for all of those, I'm using the 180 degree rotation. So that transformation has its patterns for any of those problems. And so all of them, for the cycle codes, all of them have the X. At least one X. So here I have letters that repeat twice. So the number of repetitions 2, and I have 2 letters that repeat twice. Here, number of repetitions 2, and I have 2 letters that repeat twice. These are the same. Both have two A's and two B's. This one, I think it's a better example. I have the A, B, C, and D repeat 2 times. So number of letters that repeat 2 times is 4. And then the E repeats only 1 time, and I only have one letter that repeats that amount. All right? For this other one, I have all the letters repeat twice, right? So I have 1A, the B is repeated, the C, the D, the E, the F, the G, and the H. All of them are repeated. I have 8 letters, and all of them are repeated twice. So number of repetitions 2, and I have 8 of them. You see? If I were doing, let's say, in the triangle, if I were doing the reflection, that reflection as one of my transformations, if I apply that rotation to this vertex, it goes to itself. That closes my cycle. So now I choose a different letter for another vertex. And if I reflect it above a line, it goes to this vertex. So I label it the same. And if I reflect this vertex, so same transformation, it goes back to the original. That closes my cycle. So those are these. For this picture, is the same thing. That's an A. Those are B's. Again, same transformation. That reflection. For this picture, A goes to A, B goes to B, C goes to C, and D goes to itself. Right? If I reflect, the D goes to D. And for this one, A goes to A, B goes to B, C goes to C, D goes to D, E goes to E, F goes to F. So if you reflect E, it goes to the other E. If you reflect that one, it goes back to the E. So that's my cycle. And so for the cycle codes, look, here I have letters that repeat once and twice. Here I have letters that repeat, I write the exponents in the second. So once and twice. Here I have letters that repeat once and twice. Here I have letters that repeat once and twice. How many? Well, I have one letter that repeats once, and I have one letter that repeats twice. So you can think of this one as accounting for the B, and this one accounts for the A. A repeats once, B repeats twice. Mm-hmm. So this one is the same because I have the same letters. Here I have 2 letters that repeat once, 2 letters that repeat once, and so here I'm talking about A and B. 2 letters that repeat once, and 2 letters that repeat twice. So those ones will be B and C. Mm-hmm. Remember, the subindex is the number of repetitions. The exponent, so go with this. The exponent is the number of letters that repeat that amount. Mm-hmm. And so in this last one, I have the A, the
Wait,
B.
sorry. Is that B here? Or is that D?
In this one, those are B's, and the last one is B. B goes to itself.
That's a D?
Yeah.
Oh, okay, so then that would explain the A and D with those are 2 letters, but they only appear once. So, okay, that's okay.
Yeah.
I wasn't sure if it was a B because then it would be 3 B's and 2 C's. So. Okay.
But it wouldn't be a B, right? Because we're looking at the reflection. And when you reflect this B, it goes to the other side, right? You get the second B. And when you reflect that one, it goes back. That closes the cycle. This B never goes to the other places. It just goes from its original place to itself because the reflection takes it to itself. So this should be a different.
Yeah, for me it was just hard to see the letter properly, so I wasn't sure.
Yep. So here, letters that repeat once, A and B. There's 2 of them. So this is because of A and B. And letters that repeat twice, all the others. So B, C, E, and F. 1, 2, 3, 4. 4 of them. Mhm. So that's all the other letters. It's B, C, D, and F. B, C, oh, is it not? B, C, oh, no, not B. B, C, E, and F. 4 of them. Mhm. And in the table, a good thing to check that your cycle codes, it's not a foolproof, but at least it might catch some mistakes. So something you can do is multiply, so these are just checks. This is like the last column of the table. If you do subindex times exponent, and you do the sum of that, it gives you the total number of objects that you're coloring. So like in this triangle, I have 3 objects, and in my check, I do 1 times 1 plus 2 times 1. So index times exponent, and that's a 3. Same thing here. Here I have a 1 times 2 plus 2 times 2. That's 4, 6. That's 6. That's the 6 circles or balls or whatever they are that you are coloring. This is 1 times 2 plus 2 times 4. So that's 10. Those are those 10 circles. That's the last column of the table. And so you see, even though we didn't do any problem like this in class, you have everything. So I can change the figure a little bit, especially given that we have already too many examples. I need to find something that's not like straight from the examples that we have. But yeah, there you have some possibilities. Maybe we should try do one of the cube ones with pictures, because in the forms I don't have any pictures. Mm-hmm. Questions up to here? Okay. So let's see. So here I have copies of the pages.
Professor.
Yeah.
Number 74.
Mm-hmm.
How did you do this one? Is the last line.
Okay.
You are adding M1 equal to M2 equal to 6. Why you are choosing M1 equal to M2 equal to 6? And how did you get the coefficient of this?
Okay.
Okay.
Then we'll do that. Let me just I made pictures too. I have some pictures ready. So let's see. Which one was 77? This one. Okay. So for 77,
it's 76.
Oh, 76. This one. All right, okay.
Oh no, 74.
That's 4. Okay, this one. Easier for me. Okay, thank you. Okay, so maybe let me paste my picture for 1 second, and then I'll go back to the cycle codes. Let me first go to Farida's question, which I think it's a question that a lot of people have, because for the most part, all the submissions that I read were okay, but some of them had troubles in that last part. Figuring out what's the coefficient of whatever you need. Okay, so let's say that your pattern inventory is already okay, right? So let's say that this is correct, and here we're looking for the coefficient of A1 to the 6. A1 to the 6. Actually, I use B's and R's, huh? I should have written, I guess, B to the 6, R to the 6, because I replaced so here, A to the 6, B to the 6, because I replaced my A1 and A2 by B and R, right? Oh, then again, this is R to the 6. Anyways, so here's my pattern inventory, and I want to see what's the coefficient of this. Now, again, if you can copy this, let's say in Wolfram Alpha or someplace else that you like, and just ask the system to expand and see what is the coefficient of of this. I realize that I'm not writing the right letters. B to the 6 at the
Professor,
6.
can we use the Wolfram Alpha on the files, and are we gonna still get the same grade?
If the number is correct, yes. But you see, if you just give me the number because you use a system and your number is not correct, then, and by I mean by correct is consistent with this, right? Because this might have a mistake, but I said that you can get the points as long as you're consistent with the previous word. So as long as you're consistent with this and you have the right number, perfect, right? You get the points. Now, if there is a mistake, I cannot give you partial credit. If you try to do this and I see a mistake in one of these terms, you can get partial credit. So there's an advantage to try and do it this way. In terms of partial credit, if your number is correct, then that's fine. All right. So how can I get this b to the 6, r to the 6? Well, if you were to expand this, you could do it using Pascal's triangle, right? You have b to the 12 plus b to those 12 times b to the 11 times r, and so on. You can use Pascal's triangle. But we know that the coefficient is just of b to the 6, r to the 6 is just 12 to 6, which more generally, for, if you have more than two variables, you can just write like this: 12 choose whatever the exponents are, 12 choose 6, 6. This is the same as 12 choose 6, which comes from Pascal's triangle. So this just goes for that one. Now, this one, if you were to use Pascal's triangle again, for b to the 4 plus r to the 4 cube, if you were to use Pascal's triangle, this is the coefficient of b to the 4 cube, r to the 4. This is the coefficient of
This one is 0 is okay, but my third term is I'm thinking 3 times how it becomes 6, choose 3, 3.
That's what I'll get to that one. So I want to explain first why this one is not, it's not going to give you that b to the 6.
Like b to the power 6 or r to the power 6. The second term cannot give this one.
This one is not going to give you b to the 6, r to the 6.
Right? But third one will give us b to the power 6, r to the power 6. But my confusion is here 3 times. When you are writing 6, choose 3, 3. And this part is a little confusing to me.
Okay, I'll get there. Farida, give me 1 second. Okay, so if I use Pascal's triangle, or the binomial theorem, I get that, right? And so when I get that, you can see that all my exponents, once I reduce them, are multiples of 4, right? So this 3 times 4, 12, 4 times 0, 4 times 2, that's 8. All of them are multiples of 4. All exponents are multiples of 4. Therefore, so there is no b to the 6, r to the 6, right? And so that's why we have that 0. Now for the next one, this 6 choose 3, the 6 choose 3, 3 is the same as 6 choose 3.
Okay, then it's okay. This part I got it.
So the reason why I'm writing it like this,
So
which
if we in the first term, if we write 12 to 6, it will be okay, or we have to write
that
them
would be
12.
okay, but if you have more than two colors, you will need to use the multinomial coefficient, right?
Okay. Oh yeah, I got it. I'm sorry.
Yeah.
But why these terms will be 2 choose 2 and then 0? Why? This part is little confusing to me.
That's the same as 2 choose 2, 0 is the same as 2 choose 2, and is the same as 2 choose 0. This
Why?
look, just maybe this will help. If you have n choose k, we have a formula for that, right?
Right.
If you have n choose a comma b, you need to have a plus b equals n. So that's one of the conditions so that this symbol makes sense. And the formula is just this. That's the formula for
This one I know. Okay.
So this is the same as n choose a, right? Because maybe I should write it like this. Because of this, my b is n minus a, right? So this is the same as a factorial times n minus a factorial, and also the a is n minus b. So this is the same as n choose a, but it's also n factorial over b, n minus b factorial is the same as n choose b.
Got it.
The only reason why I'm using this, this notation instead of that notation is because it generalizes to multinomials. So if you have 3 colors, then you're going to have 3 numbers, and there is no shortcut for that one as there is for the n choose k. Make sense?
Yeah, this part okay, I understand. But I need another confusion is about the pattern. Like in age 77, I don't understand the pattern you are writing: A B C D A B B B C C. I don't understand this part.
Oh, question.
Okay, so give me 1 second. Yeah, Sean.
Oh, I was just wondering, for like five
That one?
choose 2, 3. Does that mean like we could do it 2 ways? We could do 5 choose 2 times 5 choose 3, or we should do it this way.
So let me tell you where that comes from. So I have the last term. Let me copy that. Maybe I should do it with. I think I mixed my letters there. But let's do. I'll fix that one and I'll upload it again because I was mixing A and B and B and R. But these are supposed to be in B and R. So I have that, right? That's supposed to be my last term. You see? So how can I need 6 B's, and I need B to the 6, R to the 6. So I need 6 B's and 6 R's. So how can I make that? When I write those, that 2 times 2 choose 0, that goes with maybe let me move it over here. Let me move it so that it goes with this. So 2 choose 2 0 times 5 choose, what did I write? 2 3. You see, this means that I'm taking 2 B's, so a B squared from this one. This one is B squared plus 2BR plus R squared, right? So this is the coefficient. So this is the coefficient of B squared R to the 0. There's the 2, the 0. B squared R to the 0. So here I have a B squared, right? And this one is the coefficient of b square r square cube. So this one is b squared, and this one is b to the 4 r to the 6. And combined, it gives me b to the 6 r to the 6. Make sense?
Professor,
Yeah.
in same question, why you are picking M1 equal to M2 equal to 6?
Why am I picking what?
Oh.
What was that?
So
Because
Where is that? What is that?
like in 74, number 74, last the answer, when you are writing M1 equal to M2 equal to 6, why you are picking M1 equal to M2 equal to 6?
Oh, that's because we wanted to have that comes from here. So we're solving this problem where each color needs to appear 6 times. So color B appears 6 times, color R appears 6 times.
Okay.
That's where the 6 and the 6 comes from. Yeah. So Sean, were you asking something about this?
yeah, I was asking about this part. We can't evaluate it to be 5, 2 or 5 factorial divided by 2 factorial times 3 factorial, or evaluate that further to equal 5 choose 2
That's 10.
times 5 choose 3.
Yeah, that's 10. And this is 1. So all of this is 10 times the 6 is 60. But you don't have to evaluate it, all right? So if you leave your answer like this, that will be fine. But that's where the two. Okay, so look, this is one way. So just to finish up my explanation for that one, this is one way to get b to the 6 r to the 6. The other way, this one's always come in pairs, right? Because it's going to be b squared to some power. So when I multiply the exponents, it's going to be even. So I can only get b squared, b to the 4, none, b to the 0, b squared, b to the 4, b to the 6 I can't because it's only to the, actually b to the 6 I can only get even numbers from here, right? Even exponents. And so because I need b to the 6 r to the 6, I also need to get an even exponent from this one. So either 0 or 2, right? So one way to make the b to the 6 r to the 6 is getting b squared from that one. Another way to get it is to have 2, 0, 2. You see, this one will give me r squared, right? b to the 0 r squared, that's r squared. And so from the other one, I need to get r to the 4. And to get r to the 4, I need to square the r squared. So this time I need to get 2 r squares to get the r to the 4. And because these two numbers need to add up to 5, that should be a 3. So this is b squared cubed. And so now this one is b to the 6 r to the 4. And together, it gives me the r to the 6, b to the 6 r to the 6. So let me erase this one because I really don't want to, I just want to work with this part. So you see, I have these two ways. I can do this and I can do that. And that's the reason why in my counting, I had this, the 6 comes from the term, that term had a 6 above. And these 2 is because I can have 2, 2, 0, 5, 2, 3, as in here, or I could have 2, 0, 2, 5, 3, 2. But since they give me the same thing, I just place it as a 2. But it really, I could have 6. I could have 6 times this plus 6 times that, and this is actually 6 times 2 times 2 to 0. 5, 2, 3. Because this one and this one are the same. That's where that 2 comes from in that last term. But in all of them, if I actually go back now, you see, how can you get from this one, how can you get, I was using the wrong letters, but a to the 6, b to the 6. How can I get a to the 6, b to the 6 from here? Well, I need to square that one, and I need to square that one. So that's why I have the cube. A cubed square, b cubed square. That would give me the b to the 6, a to the 6, b to the 6. And then the 8 that's outside. How can I make b to the 6 here? I will need to cube the b squared. That's why I have a 3. And I also need to cube the r squared. That's why I have a 3. And this is probably one of the harder ones because all the others, this one is one of the harder ones. This ones are easier. This ones are easier. We can probably take a look at another one. Let's see. There's another one that is this one. So this one is for three colors, right? So one color appears. Each color appears 2 times. We're coloring 6 objects. Each color appears twice. That's what this means. And so I need the coefficient of a1 squared, a2 squared, a3 squared. So to get, I will need to square that one, and square that one. So that's my big exponent. Choose 2, 2, 2. Because I need to square that one, square that one, square that one. But then, how can I get a square, a1 squared, a2 squared, a3 squared from this one? It's never going to happen because all of them are going to be multiples of 3, all the exponents. So that's why I have a 0. How can I get a square from this one? You see? These terms are going to be like a1, a2, or a1 squared, a2 squared, a3 squared, a1, a2, a1, a3, a2, a3. But these ones are always even. These ones are always ai squared or ai to the 4 when I square this. All of the exponents are even. So, but because I want to have squares here, then I need to get the squares from this one. But only 2 of them are square. Only 2 of them. When I square this, I only get the double products or the square of each one of them. So the square of each one of them is going to be power 4. The double product is going to be the square of 2 of them. So I need to get the square of the other one from this one. That's why I have 2, choose 1, choose 1 for two of the letters, a1, a2, a3. So this one right here, this one right here, that gives me a1 squared to the 0, a2 squared to the 1, and a3 is squared to the 1. And this one right here gives me a1 squared, a2 to the 0, a3 to the 0. And so all together, here I have my a1 squared, my a2 squared, and my a3 squared. So this is a1 squared, a2 squared, a3 squared. You see? So that's one way. But I could also get, instead of a1 squared from the first part, I could get a 2 squared. And then the other 2 from the other. Or I can get the a3 from the first part, a3 squared from the first part, and then the other. So that's why I have these 3 over here. This 3 right here is actually accounting by, I could have 2, 2, 0, 0, 2, 0, 1, 1, or I could have 2, 0, 2, 0, 2, 1, 0, 1. So I get my a2 squared from the first part and the others from the second part. Or I can have 2002. This is getting A3 squared from the first part, and 2110. That's from the second part. So but all of these are equal.
Okay, is that what you meant by 3 positions for the 2?
Yeah, exactly.
Basically, wherever you put that 2 will decide where the other ones go for here.
Exactly.
Okay.
Yeah. So instead of writing this plus that, each one times 3, because the first 3 is just this number here, instead of writing 3 of them, I just write that times 3 because all of these are equal. So that's where that 3 comes from. That's where that 3 comes from. Mm-hmm. But again, I guess what I will do in the exam is, just enter your polynomial someplace, get the coefficient, give me the number. If that number is okay, you're done. But if there is a mistake for some reason, if you try to give me, at least part of this, if that number is wrong for some reason, then at least you can get, if you get this one right, or this 2 right, even if that one is wrong, you can get some partial credit. So I guess that's what I will do. Use a system to get the coefficient, and try to do this as much as you can, just in case, to be able to get some partial credit. Which, by the way, before we finish, we usually have 75 minutes for the exam, but because we actually have the 2 hours allocated to us, what we'll do is I'm going to be those 75 minutes connected to Zoom as usual. Mm-hmm. But then you're going to have the other 45 minutes to upload. So you can keep working on it, but please make sure that you don't go past 12:15. I won't take anything past 12:15 because as it is, you already have more time, right? This is supposed to be a midterm. So, but since some people struggle with time, let me just add this here in my notes for the exam. This is,
Is the time for the final exam 11 a.m. and we only have till 12:15?
No. It's our allocated time for the final exam, and we're supposed to keep those. Nobody is supposed to move them. No class is supposed to move them. For us, it's 10:15 to 12:15. And I didn't decide that. That was decided before the semester started by the university. And so I'll connect to Zoom. Connect to Zoom as usual. 10:15 to 11:30. That's like a regular period, right? And let's say that we're just being generous and you have 45 minutes to upload, but do not upload after 12:15. It will be closed and you don't want to risk it. I just want to be fair to everyone. I don't really, I don't want to be the bad person who doesn't take anything that's late. I just want to be fair to everyone else. If somebody made the effort to have it on time, even if they could use 5 more minutes, then another person shouldn't have the advantage of actually, emailing me to me 5 minutes later and still get credit. So please don't go past 12:15. Okay? Upload no later. And that's very important.
Kind of a bummer though. It's like if you're given 2 hours to work on the exam, but sometimes that app, my current Adobe Apps app, Scan app.
Not really, Sean. I'm giving you 75 minutes to work on the exam. If you want to risk it,
oh, okay.
So the exam is not going
to take the full 2 hours.
The exam is supposed to be for 75 minutes. That's how I'm deciding it.
Okay,
I'm just trying to be nice, and I'm giving you 45 minutes to upload, which is,
okay. I was
in fact, you know what? You can upload several times. So what I will do, because I'm not taking anything late, again, I'm not trying to be that bad person. I'm actually trying to be a good person to people who do things right, which
Okay.
usually happens unnoticed. But I want to be that good person. Be fair to those who do things right. So I won't take anything after 12:15. You have 45 minutes to upload. So please, don't risk it. Upload something after the 75 minutes, and then you can keep working on it. And if you have something better, upload it again. And if for whatever reason you're trying to upload your best version at 12:13 and it doesn't happen, you still have everything else, which is fair because you were supposed to have 75 minutes anyways, right? So
Okay.
no excuses. Please, 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 no excuses. I'm trying to do the right thing for people who do the right thing. All right?
Okay. Well, hopefully,
Okay. So,
yeah. So hopefully my app will be fine because lately after the update, the picture quality for my scan app is pretty poor.
well, you have a lot of time, Sean. Let me see. Gomez, you have a question.
Just double checking exam is managed to be 75 minutes in general.
Yeah.
Guys.
Yeah.
Okay. Just double
Yeah,
checking.
so I'm thinking about it as being 75 minutes. So I'm not trying to make it longer because we have 2 hours. No, I'm trying to give you some extra time just in case. But please, you can upload as many times as you want. So do as I said, just upload something that you feel is good enough. And then you can keep working. And that way you don't risk it. In any case, you can just improve, right?
Okay.
So,
Professor?
However, having said that, try to title it in a way that I know what's your final version, so that I don't start creating something that's not the one, right? Yeah. There was another question.
Sorry. Just quick question on the plenarity. On the second part of the exam. These kind of questions, something we can study on maybe would be quiz 7 that we did.
Yeah.
Those questions will
So
be.
for this, look at quiz 7 solutions, but also look at the class notes because during class, I solved several problems that were not part of the homework because I already solved them, right? So you can get more examples from them. And for this one, look at the solutions I uploaded this morning. Vicky said 3 solutions. I uploaded them this morning. If you see some mistakes, like I just noticed that I changed the A's and B's and B's and R's, I'll fix that. But if you see something else, let me know and I can fix it.
Thanks so
because
much.
I'm rushing. Okay. Anything else?
Professor, the exam will start at 10:15 a.m.
A.m. Yeah, 10:15 a.m.
and 12:15 p.m. it will be ended, right?
Yeah, but remember, I'll only connect to Zoom during this time in case there are any. And please do connect because there might be a typo, there might be some clarification, and that's the only way that you'll find out, right?
Yeah.
So make sure to connect. Otherwise, you're responsible for it. I will make any announcements that are relevant to the test during that time. At 11:30, I disconnect. You can upload at any time, and then do not go past 12:15. So upload something before. That's the way to not risk it.
Oh, because I have to upload before 12:15.
Yes.
Okay.
Yes.
I have another question because I know about my internet system during the day. It gives a lot of problem. Can I send you? If I cannot send you through Canva, can I email you?
Farida, do the same thing that you did last time. That worked.
No. I'm not telling like that.
You sent me the email before and then you upload it and then it was today. Yeah,
no. Professor, I'm telling this one. If can I send you? Can I email you?
That's what I just said. That's what I just said. But you have to upload before the time is over. So the email in general makes everything harder. So this is just like Farida. You have from 11:30 to 12:15 to upload. So
I'll
please
do that.
at 11:30. Okay.
before 12:15, I will email you first, and then if I can, that's why I'm telling you. Then I'll
No,
try my
Farida.
best to get back.
No, Farida. Upload by 11:30. If if something happens, you can email me later. But you have those 45 minutes to upload. The test is over at 11:30. Don't leave it to 12:15. Okay, upload at 11:30, and then yeah. So because again, I have to be fair to everyone. If people are taking the time to upload, you might not be the only one needing a little extra time to upload. So, if I just tell you to email me, then everybody will email me at 12:14, and then that's going to be a problem. So
it means
upload by 11:30.
Okay.
Okay?
At 11,
All right,
but why you are writing 12:15? That's why I'm confused.
What was that?
Why you are writing 10:15 to 12:15? So
I'm just giving enough time to everybody to upload. That's it. And so, if you wanna keep working and you have the chance to upload again before 12:15, that's fine. But if you can't, then you're supposed to start uploading 11:30. Okay, guys, I have to run because I have another meeting in a few minutes.
Okay,
I'll be my office hours.
Thank you very